Meet the smart map.
Okay, let's dive into this. To really understand this technology, we need to completely change how we think about maps. We aren't talking about that flat, static paper map crumpled up in the glove box of a car, right? We're talking about something living, dynamic, and highly analytical. We are essentially talking about the brain of spatial technology. Just think about these questions for a second. Where are accidents happening most often? Which areas are actually at risk of flooding? How can we plan better roads or schools? These aren't just random trivia questions. These are massive, real-world logistical problems that city planners, emergency responders, and engineers are wrestling with every single day. A traditional map can show you where a road is, sure, but it can't tell you if that road is dangerously prone to accidents, or if building a new school right next to it is going to cause an absolute traffic nightmare. To answer those kinds of complex questions, we need a system that can actually think geographically.
And that brings us to the formal definition of our analytical brain, GIS, which stands for Geographic Information Systems. This is a comprehensive system used to collect, store, analyze, and visualize data connected to specific locations on Earth. Now, I really want you to focus on the words analyze and visualize here, because GIS takes these vast amounts of raw location data and turns it into a smart map. It's an engine that processes the where and the why simultaneously. The secret to how GIS actually pulls this off is all about layers. Imagine, if you will, taking transparent sheets of paper, each containing a totally different category of information, and literally stacking them one on top of the other. A GIS map layers roads over rivers, then places population data over that, followed by land use zones, and finally underpins the whole shebang with rich satellite imagery. By stacking these distinct layers of information, GIS allows us to reveal hidden patterns that were totally invisible before. Suddenly, you aren't just looking at a river, you're looking at exactly how a specific river's floodplain intersects with high-density population zones and vital emergency roadways. It's a total game-changer for analysis. Moving right along to Section 2, Remote Sensing, or as I like to call it, Earth's Eyes. Now, a brain is pretty much entirely useless without eyes to gather information about the world around it, right? If GIS is the brain processing the data, where exactly is all this incredibly detailed, up-to-date data coming from in the first place? Enter remote sensing. This is the science of gathering information about the Earth without touching it directly. Instead of sending thousands of people out with measuring tapes, which would take forever, we use sensors that detect reflected energy from the Earth's surface. These eyes in the sky take the form of satellites passing over the Earth, aircraft flying high above, and specialized drones. Through remote sensing, we can continuously observe massive expanses of our planet. We're talking everything from tracking the health of dense forests and vast oceans, to monitoring the sprawl of cities, shifting weather patterns, and long-term environmental changes. It is a constant, unblinking observation of our world. Which brings us nicely to Section 3, the perfect synergy. So, we have GIS, the analytical brain, and remote sensing, the watchful eyes. Separately, both of these are impressive scientific feats, but together, they create this perfect synergy that allows us to not just observe the world, but to actively manage it in real time. Remote sensing is entirely responsible for the raw data. It captures the pristine images and the crucial measurements from those satellites and drones. But, let's be honest, raw data is just a pile of numbers and pictures until somebody organizes it. And that's exactly where GIS steps in to handle the analysis, organization, and the generation of actual usable insights. One technology gathers the raw visual measurements, and the other organizes it to find actionable answers. Let's look at exactly how this plays out in a real high-stakes scenario. Imagine a serious emergency scenario. A massive flood suddenly hits a populated region. Total chaos is unfolding, waters are rising fast, first responders are completely blind to the true scale of the disaster on the ground. Communication lines might be completely down, and they desperately need to know where to send rescue helicopters and boats. Now, what's really interesting about this is how we can break down the exact unfolding rescue procedure using our two systems. Step 1, high above the clouds, satellites immediately capture updated images of the flooded areas. This is our remote sensing hard at work. Step 2, those raw vital images are rapidly imported into our GIS software back on the ground. Step 3, the GIS system instantly layers that new flood imagery over its existing data of the town. It automatically calculates exactly how many specific roads, houses, and communities are currently underwater. Within literally minutes, responders have a precise calculated map of the impact zone. This synergy absolutely saves lives. Let's look under the hood in Section 4, the Spatial Toolkit. To make miracles like that disaster response actually happen, professionals in this field rely on a very specific set of underlying mechanics. Let's briefly slow the pace down for a second and organize the technical jargon. The foundation rests on three main pillars. First, GIS fundamentals. This involves managing spatial data, coordinate systems, and understanding the difference between vector and raster maps. Basically, these are the digital building blocks of the map. Second, we have remote sensing basics, which requires a deep knowledge of satellite imagery, sensor calibration, and how to accurately interpret those images. And third, because, we can't do absolutely everything from space, we have GPS and surveying. This is the absolutely crucial function of putting boots on the ground to collect hyper-accurate location data in the field. This helps us calibrate and verify our aerial systems. And this brilliantly illustrates the second half of the toolkit, which handles what happens after the data is collected. We have spatial analysis, involving techniques like buffering, data overlays, and analyzing terrains or road networks. Then there's digital image processing, where raw satellite images are mathematically enhanced and classified so computers can understand what is a tree versus what is a building. Finally, WebGIS and mapping takes all of that heavy, complex processing and transforms it into the lightweight, interactive online maps and applications that you and I can easily pull up on our phones to find out the fastest route to work or just track a delivery package.
Finally, let's look at the big picture in Section 5, solving real-world problems.
So, we know how the brain and the eyes work, we've seen them tackle a flood, and we understand the technical toolkit. Let's scale this up. When you apply this technology on a global scale across multiple industries, the impact is absolutely staggering. In urban planning, GIS and remote sensing are being used to literally design the future, creating smarter cities and highly efficient transportation systems that drastically reduce traffic and carbon footprints. Out in the fields, agriculture relies on these maps to monitor crop health and precise irrigation needs from space. We're talking about sometimes saving millions of gallons of water per farm, just by telling farmers exactly which zones need watering. And for our environment, these invisible systems act as our planet's greatest defenders. They meticulously track deforestation, pinpoint industrial pollution, and measure the real-time effects of climate change. Furthermore, the profound, life-saving potential of these tools becomes undeniably clear during our darkest hours. In disaster management, spatial data coordinates the response to massive earthquakes and tracks the devastating paths of the California wildfires, actually predicting where the danger will spread next. And in public health, spatial mapping is a primary weapon used by epidemiologists. They use it for mapping out dangerous disease outbreaks and analyzing exactly where vulnerable populations lack critical healthcare access. It is truly the backbone of global crisis response. We've moved so far beyond simply finding our way from point A to point B. By combining the analytical brain of geographic information systems with the ever-watchful eyes of remote sensing, we have built a powerful, dynamic mirror of our own planet. We can see our impact, manage our crises, and plan our future with unprecedented clarity. So I want to leave you with this final thought-provoking question to ponder. As this technology becomes even more advanced, as the sensors become sharper and the data